Hi, good afternoon, everyone. I'm Lynn Markey with the Coalition for Life Sciences. I'd like to welcome you to the 20th season of the Congressional Biomedical Research Caucus presentations. I'd like to thank the co-chairs of the caucus. That would be Representative Brian Bilbray from California, Representative Mike Castle from Delaware, Representative Rush Holt from New Jersey, and Representative Jackie Spear from California. It is because of their commitment and dedication to the advancement of biomedical research and to their ongoing support of the caucus that we are able to continue with our presentations on a yearly basis. I also would like to thank the Howard Hughes Medical Institute for its support of a generous grant which helps fund and pay for our lunches. I also want to point out that we do videotape. You see Hemming, we videotape every briefing. You can find past briefings at the CLS website at www.coalitionforlifesciences.org. You can also register for our RSS feed in order to be alerted to future postings. Now finally, I'd like to introduce Dr. David Brenner. He is from Columbia University and focuses on the developing mechanistic models for the efforts of ionizing radiation on living systems. Both at the chromosomal level and at the animal or human levels. He divides his research time roughly equally between the effects of high doses of ionizing radiation and the effects of low doses of radiation. He is the author of 2 books on radiation for the layperson. He is a recipient of the 1991 Radiation Research Society Annual Research Award and the 1992 National Council on Radiation Protection and Measurements Award. As well as being director for the Center for Radiological Research, Dr. Brenner is the director of the Radiological Research Accelerated Facility and the principal investigator for the Center for High Throughput Minimal Invasive Radiation Biodosimetry. Did I say that right? It's a mouthful. So at this time, I'd like to turn it over to Dr. Brenner.
Well, thank you, and thank you all for coming. So yeah, just who I am. So I'm the director of the Center for Radiological Research at Columbia University, which is actually the largest radiological research center in the world right now. And the oldest. It was founded, in fact, by a student of Marie Curie back in the 1920s. And I'm actually only the 4th director since then, so we have longevity. So our topic today is airport screening, very, very topical. The first of the new machines was installed in Boston just a week or so ago. So I'm going to talk a little bit about what this imaging technology is in the general terms, and the concerns that we have about the risks associated with mass screening. So, let me see. Yeah, so we're talking about backscatter imaging, and backscatter imaging is used in all sorts of different scenarios. And basically, the idea is you aim some waves at the thing you're interested in, and in this case, it's laser satellite imaging. And what you look for are the reflections of those waves coming back to you. And on that basis, in different ways, you can reconstruct the structure of the thing you aimed at. In this case, these tall buildings. Another example is actually sonar. Here's the ship bouncing some sound waves back from this submarine and getting information about the submarine. So the imaging technologies we're talking about are essentially this. You send some waves out, you bounce them back off the thing you're interested in, which is the individual's surface, and try and reconstruct an image from that. So what sort of wavelengths would you be interested in for personnel screening? Well, there are actually 2 different technologies that we're going to talk about briefly. One, whoops, not terribly visible, but here's millimeter wave, and here's X-rays. And basically, these are actually part of a whole spectrum of waves called the electromagnetic spectrum, which includes visible light and radio waves and X-rays and UV and ultraviolet. They're all actually the same sorts of waves. The difference is in the wavelength or the frequency of the waves. You know about wavelengths and frequencies just from tuning your radio to different wavelengths. So this is a very broad spectrum of wavelengths. going from very long wavelengths to very short wavelengths. And essentially the difference between these is the amount of energy that's being carried. What waves do, in fact, is carry energy from one place to another. And the amount of energy that's being carried actually increases as you go down this table here. So X-rays are more energetic, essentially, than these millimeter waves. So here's a little video, actually, from one of the companies of what goes on in the millimeter wave screening technology. Basically, you have detectors, you have emitters and antenna inside this little capsule here. And they wrote you stand still, and they rotate around you, and ultimately you get a three-dimensional image of the surface of the body. And the sorts of images that we get, or that they get for millimeter wave look like this. And in principle, it's pretty easy to detect something like explosives or a gun. And the corresponding X-ray backscatter technology, basically you stand with your hands up in between two big boxes here. And essentially the same thing happens, that you get X-rays are bounced off both the front and the back of you, and you get images which the viewer can see. And these are actually, how would you put them, blurred images, essentially. There are a whole set of different issues which I'm not going to talk about today, about privacy, that you probably are aware of, that not really in my sphere of understanding, so I'm not going to talk about those. But these are blurred images in which all the details have been removed of the individual, but hopefully enough information still to detect any explosives or any metal devices. So we've got these two different technologies essentially doing the same thing, bouncing waves off the body, measuring the reflected waves, and basically creating an image. I'm going to talk mostly about the X-ray backscatter technology, because that's the one that is being thought of for most deployment in the next year or two by the TSA. So we have concerns about the safety of X-rays in general. And why is that? Well, remember your high school physics. So here's an atom. So here's a nucleus, and here are electrons orbiting around that atom. That's orbiting around the nucleus. So what happens when an X-ray comes along? Well, basically what an X-ray can do is knock electrons out of these atoms. So here's an X-ray that came along, and the electron which was here got knocked out of the atom, and the X-ray bounced on and can actually do this to more atoms. And that process is called ionization. And ionization is a process of knocking electrons out of atoms. And that's essentially the process which is biologically harmful, because if you can knock electrons out of atoms, you can distort atoms, you can break molecules. And what's important here is that X-rays can do this, but other types of radiation, such as the millimeter wave radiations, can't do this. They don't have enough energy to knock electrons out of atoms. And that's why we're particularly concerned in general about biological effects of X-rays, because they can ionize atoms in a way that radio waves or millimeter waves or UV or infrared cannot do. So inherently, they are significantly more biologically hazardous than the millimeter waves. So, yeah, X-rays are very effective at breaking molecular bonds, and we're particularly concerned, of course, about molecular bonds inside DNA. And so what that can lead to with X-rays is damage to our chromosomes. And what we believe the general model of how cancer occurs is that chromosome damage in a single cell is the first of many, many steps that ultimately lead to cancer. So the first step in the road to a malignant cell is that the chromosomes get damaged, and then many other things have to happen over typically a couple of decades till ultimately you get a tumor. And certainly not all chromosome damage by any means ends up in a tumor. but chromosome damage is the necessary first step for a tumor. I'll show you a couple of pictures here of chromosome damage from our own work. These are actually radiation workers. This is a chromosome spread from a radiation worker. So, as you know, we have 23 chromosomes, and what we've done here is paint every one of those chromosomes a different color. So there are 23 different colors here. So in a normal set of 23 chromosomes, what you'd see is 23 different colors. But what you see in this picture, you see this purple and blue here, and you see another purple and blue here. So what has actually happened in this case is the radiation has broken this purple chromosome and this blue chromosome, and then the cell is actually very good at repairing chromosomal damage, and it does its best to join up the right ends. But what has happened here is that the purple piece has joined up with the blue piece, and the blue piece has joined up with the purple piece here. So now we have chromosomal damage, and this is called a chromosomal translocation, because some genetic information is now scrambled between this chromosome and this chromosome. And again, that's one of the first steps that we know of that leads to cancer. And so that within a chromosome, you can get damage too. So what we've done in this case is we've taken a single chromosome. This is our chromosome number 5. And we've basically barcoded it. We've painted a series of colors along the length of this chromosome. Now, I'm not sure we can quite see here, but there is one band here, this purple band, which is simply missing in this case. So what's happened in this case, again, this is a radiation worker, is that the chromosome was broken. A piece of the chromosome actually got lost, and then it joined back together again. And again, this is the sort of damage that is the first precursor of a cancerous cell. So what we're going to be concerned with today is risks of very low doses of radiation. We're not talking about high doses. We're not talking about what happens in a nuclear device or even what happens in a CT scan. We're talking about much lower doses than that. And so we really have a problem in the scientific community figuring out what the risks really are at very low doses. And the story is this. So here's a graph relating radiation dose to radiation-induced cancer risk. So what we know, often from atomic bomb survivors, but from lots of other sources, are some risks at moderately high doses. But that's not what we really want to know about in this scenario. We want to know about risks at very low doses. We want to know what the risks are down here. And we're not in a position, essentially, to be able to measure that in any direct way. The size of the population that you'd need to do that study is probably larger than the population of the Earth. So you simply can't directly measure risks at these very, very low doses. So basically what you have to do is somehow extrapolate these relatively high dose risks down to low doses. So we have a point here. We know if there's no dose, there's no risk. So we know this point here, and we know these points here. But what sort of line are we going to draw between the points up here and this point down here? Well, you can actually draw lots of different lines, and the nuclear power industry would like to draw one line, and the Greens would like to draw another line. The nuclear power industry would love a line like this, where the risk is actually 0 at low doses and then starts to increase. So what radiation research is about in many ways is trying to figure out which of these is the most reasonable risk estimate, because the data are here, what we want to know about is here, but all these different curves would actually give you very different risks at very low doses. And this curve here, actually, that's a hormetic response, where low doses are actually good for you. And I don't believe for a moment that's true, but some in the nuclear power world might. So which of these curves do we think is the most appropriate one? Well, most of the agencies and regulatory agencies have basically said, and I think with good reason, that the most appropriate curve to put through these is a straight line. So put a straight line through the data points that you have at high doses and down to 0 dose, 0 risk. And that has implications. If you've got a straight line relationship between dose and risk, well, if you halve the dose, you're going to halve the risk, and if the dose is a tenth, the risk will be a tenth. But correspondingly, there's no dose, if you use this extrapolation, at which the risk is actually zero. The dose gets lower, and as the dose goes lower and lower and lower, the risk gets lower and lower and lower. But it never goes to zero. It just gets smaller and smaller. So if you have a tiny dose, you'll have a tiny risk. And if you have a large dose, you'll have a large risk. But I do put this comment in here, but this is really the area that's most in need of research in our field. We're never going to be able to measure the risks directly at these very low doses. We're always going to have to extrapolate from higher doses. And in order to figure out which is the right curve, we really have to know detailed mechanisms about what is going on. So the implication of what I said is that we're all kind of equally sensitive to radiation, but of course we're not. And in fact, there are different populations who have actually very different sensitivities to X-rays. And the most important one is children. And children inherently are more sensitive to radiation than adults are in terms of radiation-induced cancer. And the reason for that is pretty clear. I mean, what is cancer but a disease of dividing cells going wrong? And children, of course, have more dividing cells than adults do simply because they're growing. So they have a bigger proportion of dividing cells. So children inherently are more sensitive to radiation than adults are. And the ultimate child, if you will, is the developing embryo and fetus. And sure enough, the developing embryo and fetus is even more sensitive to radiation than children are. So those are a couple of very obvious populations that are going to be more sensitive than average to radiation exposure. But they're certainly not the only ones. What we believe is that perhaps 5% of the population, so probably a couple of people in this room, are particularly sensitive to radiation, essentially for genetic reasons. And there are a few of the genes that we know about, and a couple of the ones that we know most about are BRCA1 and BRCA2, which you know of course, in the context of breast cancer and ovarian cancer. People who have women who have defects in BRCA1 and BRCA2 are more prone to breast cancer and ovarian cancer. And why is that? Well, it's because BRCA1 and BRCA2 basically are genes that deal with repair of DNA damage. And what do we want to do after radiation exposure? Well, we want our genetic machinery to come along and repair the radiation damage. So it's not surprising that BRCA1 and BRCA2 folks are more sensitive to radiation exposure. Indeed, they are. And another gene that falls into that category is the AT gene. So those are three genes that we know about, but there are a lot more that, in fact, we don't really know about, and probably most sensitivity is due to interactions between a whole pile of genes with some minor problem in them. Totaling, as I was saying before, and probably 5% of the population being particularly sensitive to radiation. So as well as children, we've got 5% of the population who are sensitive to radiation. But we can't really identify these people. We don't know which two people in this room are the two people who are sensitive to ionizing radiation. So let's get that with a little, that was my little prelude on generally the effects of low doses of X-rays. So let's talk more specifically now about X-ray backscanners, and let's talk about the doses. So the typical average body dose that you will see quoted by the industry and by the TSA for a front and back backscatter scan is about 0.15. That unit is called a microsievert. And don't worry about it, it's just a unit of radiation dose. And that is actually a very small dose. And one of the take-home messages here is that the individual dose that one gets from an X-ray backscatter scan is very small indeed. I'm going to argue that it's actually not quite as small as the TSA and industry would have us think. And the reason for that is that, in fact, the dose is not uniform at all, because we're talking about very low energy X-rays which don't penetrate the body, because remember what we're trying to do is use backscatter. So we only need X-rays that penetrate a few millimeters and then scatter back. So in fact, most of the body in the X-ray backscatter world don't get any radiation dose at all, or essentially none. So this number here, which is the number that you see quoted a lot, is basically an average over the whole body. And that's a sort of meaningless thing, because most of the body actually isn't getting any dose at all. So you're averaging over parts of the body that aren't being exposed. So in fact, it would be more appropriate just to talk about the dose to the parts of the body that actually do get exposed, and that's the skin, in fact. So here's a little schematic of radiation dose to the head here from one of these backscatter scanners, and this orange curve here, which is basically the scalp, is really the only part of the head that's getting any radiation exposure. But it's getting about 20 times this average dose that's typically quoted. So the dose to the skin, which is really what we're concerned about here, is not 0.15 microsieverts, it's about 3 microsieverts, which is still, must be said, it's a very, very low dose indeed, but it's 20 times higher than the dose that's always quoted. So it's still a low dose, but it's 20 times higher than the numbers that you'll see quoted. So we really need to be concerned only with the skin for these X-ray backscatter units, because they're not really going to produce any dose to the rest of the body. So the question then, well, is the skin actually sensitive to X-rays? And the answer is very much so. The skin is one of the more radiation-sensitive organs in the body. And we certainly know that from many different populations who have been exposed to radiation. You can certainly see it in the survivors of Hiroshima and Nagasaki. Even those who are a long way away from the explosions and got very low doses, you see an increased risk of basal cell carcinoma. And in populations like X-ray technologists, you see an increase in basal cell carcinoma. But it's particularly a consequence of exposure, radiation exposure in childhood. And that fits into what I was talking about more generally, that children are more sensitive to radiation than adults. So we have a concern here about these X-ray backscattering machines increasing our risk of basal cell carcinoma. So let's talk about BCC, basal cell carcinoma, for a moment. Well, I'm not sure you can see them here. There's one, another one on the nose here. It's a very, very common cancer. 800,000 cases a year in this country. And the concern in the radiation world is basically what radiation does is promote pre-existing damage. So it acts as a multiplier of natural cancer rates. So the fact that the background cancer rate is so high for BCC is a concern for multiplying that number by some factor in terms of radiation risk. It occurs mostly in Caucasians in the age 50 to 70. So what we're talking about here is children being irradiated, shall we say now, aged, shall we say 10, but really not really seeing the consequences of that for many decades, because it probably won't start to any excess cancers that appear, and we'll talk about whether in a moment whether we expect there to be any, really won't appear for many decades. So we're talking about doing something now with consequences many decades in the future. The other issue with BCC, basal cell carcinoma, it's mostly in the head and neck. So, in fact, it makes sense for these scanners to not actually scan the head, and right now they do scan the head, but no very good reason to me that they should scan the head, and you can't hide any explosives on your face. So why are they scanning the head and neck? No very good reason, I think. So let's now talk about the risks. Let's get down to the nitty-gritty in a way. And the distinction I want to talk about for my remaining few minutes is an issue of individual risks versus public health risks. So the individual risk from going through an X-ray backscatter machine are very small indeed. I think that's unquestionably true. So an individual risk refers specifically to the person who is exposed to that risk. But we need to think in terms of policy and public health of another sort of risk, which is a public health risk, which is the individual risk multiplied by the number of people exposed to that risk. And suppose I'm making numbers up now. Supposing you have something which gives a risk of 1 in 1,000, a relatively small risk, and supposing 5 people are exposed to that risk. Now, none of them then will actually have the consequences thereof, so it's not much of a concern. But supposing 10 million people are exposed to a risk of 1 in 1,000, then for sure that a fair number of people will actually get the consequences of that risk. So even though we need to think about individual risks, we also need to think about how many people are exposed to those risks. If it's a small number, then it's and a small risk, and a small individual risk, then you don't have a societal concern. But even if the risk to an individual is small, if you have a very large number of people exposed to that risk, then you have a population, a societal risk. And that's really the story with these X-ray backscatter machines. The risks on an individual basis, as the TSA tells us, and rightly so, very small. But the issue is, well, multiply that by 800 million, or some very large number of people getting scans each year. So the individual risks associated with X-ray backscatter machines are probably extremely small. So if you go through an X-ray backscatter machine, you shouldn't have too many concerns that anything bad is going to happen to you. The issues are much more on a policy public health level, that if 800 million people go through a scanner, even if the risks are extremely small, you start to have a public health consequences. So a small risk multiplied by a very large number of people has the potential to be a public health or a societal risk. And that's really the concern here. It's not so much that the risks are big, they're not, they're small, but a small risk multiplied by a large number of people. So what the TSA says, and there's some truth in what they say, well, there's a lot of truth in what they say. Advanced imaging technology is safe and meets national health and safety standards. Well, it certainly meets national health and safety standards. That's absolutely true. And in some very meaningful way, it's safe. In other words, as I said, if you go through one of these machines, you don't really have to worry so much. So in that sense, it's safe. But these national health and safety standards are set up for typically for occupational exposure, where an individual or a small number of people are potentially exposed to radiation. They're in no way set up for a scenario where 800 million people potentially get scanned. So it's certainly reasonable to say that backscatter screening is safe for any individual, but that really kind of dances around the real point of, well, what about a very large number of people being exposed to a very small risk? So let's talk about risks and benefits, which is what you should always talk about in the radiation world, be it medical imaging or airport screening. The individual risks, as I've tried to stress, are very small, and you have to consider them, of course, in the light of the potential benefits of safer flying. And if you can avoid anybody getting and bringing an explosive onto an aeroplane, you've done a great thing. But certainly in the radiation field, we work under the ALARA principle always, as low as reasonably achievable. In other words, you try and get the most benefit that you possibly can, which in these terms means efficient screening, for as little radiation as you have to give to the population as you possibly can. And that really leads to the issue of millimeter wave technology. So I haven't really talked about that, other than to say it exists, and it's actually used in airports in this country right now. And as far as we know, there are no biophysical risks associated with millimeter wave technology. And of course, you can never say something is for certain safe, but I think it's fair to say that we understand why X-rays would be harmful, because we talked about the process of ionization, knocking electrons out of atoms. millimeter waves can't do that. They don't have enough energy to ionize atoms. And so if there are risks associated with these types of technologies, we certainly don't know what they would be, and we have no clear mechanisms why there should be risks. So it's reasonable to assume that they are going to pose less biophysical or biomedical hazards than the X-ray systems. So I think it's a good question why one would be choosing the X-ray technology over the millimeter wave technology. I think in this country at this very moment there are actually more millimeter wave machines in airports than there are X-ray machines. But I think that's going to change very markedly, and it's going to change very quickly over the next year. The TSA has invested pretty strongly in millimeter wave, in X-ray technology. And I don't think anybody has ever done any clear head-to-head comparisons. I mean, which is more efficient? If you look at the images that the X-ray technology produces and the millimeter wave technology produces, you'd say that they look to the naive viewer about the same. So are they equally efficient at screening? I don't think we really know the answer to that. I think some head-to-head tests would be more than appropriate at this stage. And then a decision can be made with the knowledge of the different biophysical hazards potentially with the X-ray technology and the millimeter wave technology. So there I think I'm going to summarize and then I'm going to stop. So X-ray backscatter radiation doses are very small, and the doses are primarily and almost entirely to the skin. We have no direct evidence one way or another about the cancer risks at these very low doses. But what we know about the mechanisms of how radiation-induced cancer work, we would, the best estimate we can make is that there will be a corresponding very small risk corresponding to the very small dose, and it would be entirely to the skin. So, just to raise a little flag for research, we certainly need more research, not just in this area, on the mechanisms of radiation risks at low doses. It's very controversial, as I've alluded to, because a lot of political issues involved in the future of nuclear power and nuclear waste are inherently involved in this same question of what are the risks at very low doses. Most at risk are going to be children. I think that's clearly true. But there are other radiation-sensitive groups too. And research into the field of radiosensitive subpopulations is really in its infancy. It's really only in the last 5-6 years that people have really been thinking about this very much. And it's certainly an issue in terms of medical imaging in general and radiotherapy treatment. You don't want to be irradiating people who are particularly sensitive to radiation. But we don't really know at this moment how to identify most of the people who we think are going to be radiation sensitive. And the point I've tried to stress, the individual risks of going through an X-ray backscatter machine are going to be very small, but the population risk, which is the individual risk multiplied by 800 million, if you will, has the potential to be significant. I mean, we don't know that it's going to be significant, but again, we should be cautious and proactive in implementing new technologies like this. And there really is no other technology around where we're planning to X-ray such an enormous number of individuals or do such a huge number of X-rays. And it's really unprecedented in the radiation world. And as far as we know, there are unlikely to be risks associated with the use of millimeter wave scanning technology. And again, should stress as far as we know. And there I will stop, and I'm more than happy to answer questions.
May I jump in here before the question period? I'm Representative Holt, one of the co-chairs of the Biomedical Caucus, and I wanted to thank the speaker, Dr. Brenner, for this. I think you see a good example of why this Biomedical Research Caucus series is so useful. Intelligible, accurate and relevant. It points out the relevance of the research that is sponsored, for example, through the National Institutes of Health. I wanted to thank the Coalition for Life Sciences for setting up this good series. I can't help but note, as we talk about public health, an upcoming program, actually several months from now, on the mammography controversy, where individual decisions are looked at differently than public health decisions. And I think it is, I wouldn't be surprised if you would find some overlap between that lecture, but before then, there are a number of other good lectures. The next one on the schedule is Treatment of Depression by Dr. Robert DeRubes from Penn, University of Pennsylvania. So, again, I thank you all for coming. I would also note that I couldn't help but think, as I was listening to this, of how badly we need to revive the Office of Technology Assessment here in Congress. It is the OTA, which was very active until about 15 years ago, starting about 25 years before that, dealt with a variety of issues and was particularly, I thought, contributed to the work of Congress in a particularly strong way, where the subject matter fell between committee jurisdictions, just as this does. Those who are funding the TSA may be unaware of the NIH research. The Office of Technology Assessment, I think, is just the sort of thing that we need here in Congress to help us make the decisions that fall between committee jurisdictions. Not only that, but that certainly is one prime area. So I thank you for a good presentation. I'll turn it back to you then for questions. But if I may start with a question. Yeah. There's, ever since I can remember, as a physical scientist, there has been a debate about whether exposure to radiation is linear or not, and cumulative or not. For the kind of radiation that we're talking about here, backscatter for airport detection and that sort of thing, is there any evidence to resolve this, whether it is cumulative and whether the harmful effects of dose is linear, or whether you can undergo a low level for a long time. But anyway, I'm sorry if I missed that. I beg your pardon. Okay. But maybe it deserves restating.
It does deserve restating, because it really is at the heart of the issue. You really put your finger on the real problem. We know what risks are at relatively high doses because we can measure them. We really want to know about risks down here, where we really can't measure them. We will never be able to do an epidemiological study at extremely low doses. And that's inherent. It's really to do with the fact that 20% of us are going to die of cancer anyway. So if radiation is producing a small increase over that 20%, it's very hard and almost impossible to measure it at very low doses. So you're always going to be in a position of trying to figure out the mechanisms of how you extrapolate risks that you know to risks that you don't know. And there's a lot of research being done in that area. The DOE has a low-dose program, for example. But it's quite a politicized area too, as I alluded to. Nuclear power industry certainly has a different perspective.
And where would airport backscatter dose be?
Well, it'd probably be here. It's a very small dose indeed, and so.
And by dose, you mean radiation energy within a few seconds. If you got got 10 of those within 2 days, is that a higher dose or or not?
As best we know, if you have 10 scans, whether it's over a few days or a few years, your risk will be 10 times what it was if you had one scan. And that's, I think there's good evidence for that now. Nevertheless, the risk at very low doses still is the most uncertain area. How to extrapolate to very low doses. And the Health Physics Society, the nuclear power industry, the Greens will all give you very different answers. The French will give you very different answers. They have very different views from the Americans on this. So it's unfortunately quite a politicized area, and trying to break out the science from the politics is hard. But generally speaking, all the agencies, like National Academy of Sciences, that have assessed this issue have said that the most reasonable thing to do at this point is a linear extrapolation. So there is no dose where the risk is 0, but the risk will correspondingly go down as the dose goes down.
Thank you, Dr.
Can I just add one little rider to your comments before? The issue of mammography is very much the same issues that we're talking about today. Again, it's a risk-benefit equation, and we're particularly concerned in mammography about sensitive subpopulations. We're interested particularly in women with BRCA1, BRCA2, because they're more sensitive to breast cancer, we know. But if they're more sensitive to radiation-induced breast cancer, do you want to be screening those people with X-rays? There's a balance to be had there, and I don't think we have all the information we need to really be able to make that balance right at the moment.
Yep.
Hi, I'm Elgin Fadji. I work for a member of the Homeland Security Committee, and one thing that TSA has always said is that this technology, the backscatter technology, is basically going through the machine is equated to about 2 minutes in flight on a plane. So how does that, going through that machine add to the public health or individual health risk when you're going to be on a flight at least 40 minutes,
Well,
what's the difference there?
I'll give you two thoughts on that. First of all, I think those numbers are wrong, because when you're on an aeroplane, you're getting a whole body dose. What the industry, and actually the TSA does too, is take the dose from one of these X-ray backscatters machines, which is only a skin dose. That's all you get. You only get exposure to your skin, and then they average it over the whole body, and so the number actually becomes a lot less. You should only be thinking about the skin dose, which, as I said, is typically about 20 times higher. So take those numbers in terms of time of flight, and you should really multiply them by 20 to take into account that you're really only thinking about skin dose. But I suppose in general, I'm thinking, yes, it is certainly true that flying inherently exposes you to radiation, and there is a risk associated with that. But does that mean that you should therefore be accepting of other risks? In general, we have all sorts of risks in our lives, but that doesn't mean that we should necessarily accept other risks if we don't have to. And again, the Alara principle says, let's limit the radiation dose as much as we can. And if we can use technologies that don't use X-rays, maybe we should. Yeah.
Yeah, this is not my question, but why does that one line loop down into negative y?
This one?
Uh-huh.
Ah, well, that's
But that's not my question. But
well, let me say that's called hormesis, and the nuclear power industry loves hormesis, and so basically what that would say is very low doses of radiation are good for you. In other words, the risk is a negative risk. You're actually reducing the number of cancers if you get exposed to low
It doesn't
doses.
kill you, it makes you stronger.
I actually don't think so. These are all possible curves that you could draw between these data points and the data point here, which is 0 dose, 0 risk. These are all in principle possibilities. I don't think for a moment this is true. These are certainly different curves that different people have suggested as appropriate ways to extrapolate these risks to 0 dose, 0 risk.
Thank you. And now my question. I apologize if you answered this before I rudely came in late, but is there a way, if indeed we're going to have backscatter technology and they're not going to go with the, remain with the millimeter wave scanning technology that appears to be safer. If we're going to go with backscatter across the board, is there a way to design the things so that you can protect your head and neck, or do you have to wear like a lead football helmet when you go in there? Or, I mean, is there a way to at least mitigate that risk?
I would. I mean, to be honest, I would go through the machine with a paper bag over my head. But there's no reason why these machines basically take a pencil beam of X-rays and scan it, raster scan it over your body, just like your TV screen is raster scanned. There's no reason why they should raster scan the head. They don't have to do that.
But I mean, is that an easy thing to control, or they
Absolutely.
have to redesign the thing?
No, it wouldn't be hard at all. It would not be hard at all. So that would be the best way to really minimize the risk here, because what we know about basal cell carcinoma is primarily disease of the head and neck. You do get it in other parts of the body, but not a lot.
Thank you.
I actually have two questions, and you might not be able to answer the first one, but you said that TSA is focusing a lot more on the backscatter X-ray type machines. Is it cost effective? Is that why the cost is lower to invest in those than the other machines? Or?
So the question was, why is the TSA going towards X-ray machines?
Lobby.
You're absolutely right. I don't know the answer to that question. As I say, right at this moment, there are more of the other types of machines in airports by a lot. Why they're going with X-rays? Is it that their efficiency is better? I don't know. And I certainly don't know of any head-to-head comparisons. There's certainly none in the open literature. I don't know if anyone has any comments on that question.
I think it is a cost issue. I mean, they purchased 150. They started deploying 150 backscatter imaging machines this month, and they plan to deploy up to 450 this year. So there's currently 40 of the wavelength technology machines. You can.
And now you might be able to, but eventually you wouldn't.
The idea is
No,
TSA say
you're
you
supposed
can,
to, yeah.
But of course the option is the pat down, where you'll have to stand in line and maybe miss your flight. So often it's not a realistic option if you opt out. But certainly the TSA say yes, you will be able to have a pat down.
And one lesson we should take, this should not be, as you say, a head-to-head competition.
Are there ways that you can, like she said, and what the congressman was going off of, if it is accumulative and the body just hangs on to those things and you do have an atom that, is destroyed, does the body, is there a way to repair that damage, or is it just always there? And are there things that you can do when you step in? Like, should you wear long sleeves? I mean, is there any way you can protect yourself at all?
I don't think there's, well, first of all, let me say the body is unbelievably efficient at repairing radiation damage. Unbelievably efficient. The problem occurs is that once in a while, when attempting to repair damage, it will misrepair damage. Now, I gave you an example of that with those chromosome pictures. What's happened there is chromosomes were broken. The body did its best to repair that chromosome, but it actually joined the wrong ends together. So it's misrepair of damage, which is really the issue. I'm not sure there's much you could or even should do individually going through a machine, because the risks are very, very small anyway. As I said, to my mind, putting a paper bag over your head is as good as anything. Not that I would recommend it.
You may get some looks.
Well, to an extent it would, because the X-rays are very non-penetrating. So have a thick piece of paper over your head, and it would actually stop a good number of the X-rays and reduce the dose to your face.
But how would you, could you rank, if you would, the public health risks of this sort of issue compared with mammography or aggressive medical testing, CAT scan? I mean, I know the population would be smaller, but presumably the exposure to radiation is much greater.
Yeah, you're absolutely right. most of what I do is associated with understanding the risks associated with medical imaging. And I think in the bigger picture of our world, that's a more important issue than this. And I think in terms of the population risks, we should be more concerned about the overuse of medical imaging than we should be concerned about airport scanning. But both are relevant issues. If you wanted to know which one I would say my heart is in, it's in the issue of medical imaging. The unnecessary population exposure is higher there.
Thank you very much. Thank you.
Pleasure.